Hello, my name is Dmitry. Welcome to the DPLabs channel. Today's video will be about making a gearbox for an electric motor for future projects.
So we bought, in fact, a Chinese motor, 70 kilowatts, I think that's its peak. Along with it, a controller for 400 volts, 9,000 RPM. And we need a gearbox for it with an output for the drive shafts. Of course, we could have just slapped on a gearbox from a VA's 2108 or a Nissan Leaf using an adapter plate. But that's too easy. We want something a bit more complex and of higher quality. So what we actually need is a gearbox. Naturally, we took a gearbox from a VAZ 2108, of course. From it, we'll use the differential and the final drive because the final drive is large and would be difficult to make ourselves. Well, we can also use the bearings. This will be the second stage of the gearbox, and the first stage will be made from 2 gears. That's what we actually have to manufacture now. So, we've already rough machined the blank in one setup. We'll have 2 setups in total. We left a little over half a millimeter of allowance because first of all, there will be 2 setups. Secondly, removing a lot of material at once can cause it to warp a bit. We'll bring the final dimension in the centers. The steel here is 15 K2GN2TRA. It's highly wear resistant, can withstand impact loads and hardens well. The cutting parameters here are pretty much like on the machines from a certain Chinese company that a blogger advertises. 100 RPM, feed rate 0.1, diameter 150, cutting 15 millimeters on the diameter. It's a tough steel, turned on the coolant, started the feed, came back in 10 minutes and 3 kilograms of metal had been removed. It's very convenient. Now we're actually going to flip it over. On the second setup, we'll rough it again, leaving about half a millimeter allowance, set it in the centers, and bring it to the final size in the centers. We've already machined the workpiece in the centers almost to its final dimensions. That is to say, the dimensions for the collars are indeed final here, but for the bearings, we've still left a precise allowance of about 0.3 millimeters because I think after the hardening process, we'll finish it to its exact size. Also, on this side, we have splines where the gear will be securely mounted. Here we have a groove for the tool exit, and it's rounded to effectively avoid a stress concentrator. That's because we'll have one gear positioned here and another one there, and to prevent it from breaking at this specific spot, it's better to make the groove rounded. Here we have a standard groove for a retaining ring, so that the gear can be mounted here, and there will be a bearing in this spot. As for how we'll cut the splines, we're going to use a method that's not exactly correct. Ideally, this should be done either on a dividing head or a special gear cutting machine, but we only have a slotting machine with a rotary table, so we'll be cutting them on that. Here we have a total of 25 individual splines. So for each and every one of these splines, we will need to carefully rotate it by precisely 14 degrees and 24 minutes. That means since the dial is precisely graduated in 2-minute increments, we will therefore need to make a total of 3 full turns and 144 minutes, which is exactly 72 divisions. Accordingly, our margin of error is half a division, which is about 1 minute. In principle, I think this is more than sufficient and the splines will turn out quite precise. Here, we already made a test sample, hardened the splines with induction heating, and the gear fits on. So everything is good here. The tooth profile here is 90 degrees with a rounding of about 0.6 to 0.8 millimeters. The outer diameter is 27.3 and the inner diameter is 25.5. So we carefully cut the spline, then precisely rotate the spline and also meticulously set up the part, aligning it very precisely with a soft copper hammer. We managed to achieve just 1 to 2 hundredths of a millimeter of run out here, but unfortunately it's simply not possible to get it any more accurate on the rotary table. Well, now we're actually going to cut the splines. In a completely magical way, we already have the finished internals of the gearbox, so to speak, fully completed. How did that happen? Well, as you clearly saw, we successfully made the initial blanks and then cut the intricate splines for the main gear pair. Here the splines are quite simple, precisely 90 degrees, not modular. We successfully managed to do that particular task. Next, we really wanted to cut the actual gears themselves on a sophisticated 5-axis CNC machine, specifically on the Haas. We have a very special mandrel along with modular disc cutters, but despite our best efforts, we weren't able to successfully achieve the desired outcome. I don't know whether it was the specific machine itself or perhaps the specialized mandrel that truly lacks sufficient rigidity for this particular operation. We diligently tried many different settings and various parameters, but unfortunately there was persistent and noticeable vibration, which resulted in the surface quality being quite unsatisfactory and simply not up to our high standards. So after careful consideration, we decided, plus since we also have gears for the engine that are designed to be modular as well, and I think the module here is precisely one or something very similar to that, so we ultimately decided to entrust this critical task to highly specialized experts who specifically focus on this intricate work, sending it to a dedicated gear hobbing machine facility, and they, with their extensive expertise, meticulously made and precisely cut the teeth on our prepared blanks for us, as well as crafting the essential splines that will eventually go into the engine assembly. Everything turned out absolutely great and perfectly here. Then we proceeded to harden everything with a precise induction hardening process, carefully tempered it to achieve the optimal material properties, and everything went incredibly smoothly and according to plan. Next, we meticulously finished the precise bearing seat dimensions in centers. There was only a very small allowance here, and in general the hardening process went exceptionally well. Nothing warped or deformed. There was basically no measurable run out, not even as a result of the hardening process itself, but we decided to play it safe just a little bit more to ensure absolute perfection. Then I took the entire finished assembly and together with the engine meticulously modeled everything in SolidWorks. That is, a complete and comprehensive assembly of the internal part of the gearbox, illustrating exactly how it would look and function. Of course, it's not modeled in maximum hyper-realistic detail here. For example, our main pair is still a helical gear and a differential, but here it's modeled in a somewhat simplified yet functionally accurate way. However, all the critical dimensions are set precisely and accurately, so we know all the exact center distances, we know the precise linear distances for the differentials, tapered roller bearings, and now we actually need to proceed with the manufacturing of the gearbox housing itself. We'll accomplish this on a sophisticated 5-axis machine, specifically a Haas, and in the best tradition of precision machining, we'll be skillfully turning huge solid blocks of high-grade aluminum into fine chips. Pavel has already meticulously modeled the intricate gearbox housing for us. What's particularly notable and interesting here? On this specific side, we'll have a convenient oil-fill plug. Here will be a specialized fitting for a breather, and these precisely drilled holes are specifically for mounting the gearbox. That is, this entire robust structure, detailing exactly how it will be securely attached to the vehicle's chassis. First, the motor itself has 4 robust threaded holes, so we can easily make any kind of custom bracket and attach it however we want with great flexibility. Then the gearbox has 2 additional threaded holes here, also specifically designed for a bracket, and 2 more threaded holes located here. This particular part, the flange, will be primarily used to securely attach it to the motor. Here will be our distinctive branded logo, proudly displayed. What else is there to consider? Well, we can try to visualize and see how it will look inside. There's practically no excess metal or unnecessary material here. It will be expertly made of lightweight yet strong aluminum, so it will be quite light and efficient. There are special strategically placed pockets everywhere, including on the motor side, so it will turn out pretty light and optimized for performance. That's roughly how it looks and functions. As for the differential bearings, they're tapered and will also be precisely adjusted with shims for optimal performance. Before final assembly, I think we'll just put it together without traditional gaskets, instead utilizing a high-quality, reliable sealant for a perfect seal. Now we'll show you the detailed milling program for all this intricate work and precisely how it will be machined. The programs for machining are already meticulously written and thoroughly tested, so you can clearly see how it will look in its final form. This is already the second setup in the machining process, so as you can clearly see, the first setup is already completely done and verified. Now we'll show how everything will be meticulously machined, and here is the detailed simulation of the program for the second setup of the first half of the gearbox housing.
Gentlemen, we've truly ended up with such a remarkably beautiful, incredibly luxurious piece, and in terms of significant metal savings, we've absolutely outdone Inohodu, a substantial 62.5 kilograms of D16 alloy meticulously transformed into just 4. Of course, this is merely a prototype, and naturally, if this is going to function effectively and be mass-produced, it absolutely needs to be made by casting, because the overall price is currently sky-high, both for the precious metal itself and for the intricate machine work involved. But as a functional prototype, it's exceptionally good. I sincerely hope everything with the intricate intricate gears will precisely line up here, and it will work flawlessly, and we'll ultimately get a truly decent and powerful unit, basically designed for modern electric vehicles. Actually, it wasn't that easy at all. After the initial 3D model was completed, another full 20 hours went into meticulously fine-tuning the complex tool paths, and about 2 full days were spent on the actual milling process itself. But we genuinely wanted to achieve a beautiful, exceptionally smooth surface finish. In reality, that level of perfection isn't strictly necessary, since it's just a preliminary prototype. Of course, later on, this should definitely be made by casting for cost effectiveness, but I think it turned out pretty well indeed. We'll keep diligently working, so please subscribe to the channel, give us a well-deserved like. All the very best. Goodbye, goodbye. So...